All right, so I just provided for the class a little summary, which is actually within the class notes, but the summary should contain, I think I'm missing some pages here, but I mean, you should have like, I think there's a page before this one, but you should have like this page over here with the equations that we do have the other day, which is, this one is a general form, and then this one is applying the initial conditions of x sub naught would be the initial displacement, and v sub naught would be the initial velocity. Okay? So I think on the previous page you have the equations for the underdamped and the critically damped on the first page. And here's a figure of the three of them, but I think it was a bit too much on the same figure, so I think I redid these ones in MATLAB, where you see basically the shape of the responses for the critically damped, the underdamped, and the overdamped. So let's do a quick summary. So what is the critically damped? It's when the damping ratio is equal to 1, and that corresponds to what? It will correspond in where, I mean, here we don't have the equation, but it will correspond when the radical term was equal to 0. Okay? Then the underdamped is the most classical case, is where you have a system that initially is that you let go from a certain position, and in function of time, the response is going to damp out. All right? The one is overdamped, meaning that as soon as you let go, it's just going to go to a zero displacement position very quickly. All right, and I think last time I told you sometimes it's useful to do the same thing on the phase plot on the state space representation, which basically states here you have the position, and in here you will have the velocity, or x dot. All right? That's the way it's generally solved in controls, and that's the way you generally set out the equation when you solve the equation numerically, which is what we'll be doing today. All right, so basically you see the response here. This is the big red is the underdamped position. So basically that is just going to take a while to go to the zero response. Then and you can see the shape of the critically damped and overdamped. Obviously this is for the data that I use for this case, no? But if you use different data, these two curves might have completely different shapes. Okay? They might just come back maybe at a lower rate or high rate. All right, so we'll put these pictures back here. And let's get started with an example. So let me know if you cannot read. Oh, this is way too much. I'm going to have to reduce the zoom over here. Okay, good. I don't know what I want. How can I exit this now? Here we go with the return button here. All right. You let me know if you cannot see. Or read. Okay. So let's do one example. Let me remove all these class notes. Oh, I should scan these ones to give them to you. I do that when we get close. Before the exam, whatever class notes we have, I scan them for you. So it would be, let's say, example 1, or maybe not, let's say just example. So if I follow my numbering here, this should be page 25. Page 25. All right, so we're gonna have our block over here of mass M, which is connected to a spring of stiffness K, but remember this time we have a damper over here of constant C. So something important to remember is that the damping, the viscous damping, is always proportional to what?
The velocity.
To the velocity, correct. Very good. So for this problem, let's see. Let's say our coordinate system, the origin will be here. And that we have the two initial conditions. Initially, the displacement is going to be 5, and the initial velocity is going to be 1. Okay, so for this problem, we have N will be equal to 200 kilograms. K will be equal to 1,000 Newton meters. And C will be equal to 100 Newtons meters second. Can you read? Okay, so the problem asks us to determine the equation of motion and to solve it, analytically first, and then numerically. Okay, so deriving the equation of motion should be very quick by now. So like first, you want to follow procedure 1, we first do some type of diagram. Where what do we have? This one we have the spring force, the damper force, and here we have MA or M X double dot. I don't do any modal forces on the y direction like the weight mg or the normal. We know we just care about the motion of the x direction. So 2, we apply Newton's equation, summation of forces equal to ma, and it was on x direction. So what do we get? Minus kx minus cx dot equal to mx double dot, which gives us the equation mx double dot plus cx dot plus kx equal to 2. Okay, so over here, what is the fastest way for us to know what type of response we are dealing with? Probably would be to find what is the value of the damping ratio. XC. And what was the definition for this was damping over critical damping. And maybe you have to go to a class note from yesterday, but what is a critical damping is 2 times m omega sub n. Where, okay, what is omega sub n? As you should know by now is
Square root of K over M.
square root of k over m. Okay, so over here, page 26. So we do a numerical application, this will give us XC, so let me just write it down, is C over 2m omega n. And if we look at the problem statement, what is the value for C?
100.
100, then we have 2 times the mass, which is
200.
200, and then the omega n, we do the square root of k over m, which is 1000 divided by 200. So if you want, you can check. It would be good if you have calculators to check instead of me just trying to copy what we have. So if you do this, we get a value for the damping ratio equal to 0.1118. So go ahead and check this. It's good if you work out the problems as we do them.
I agree.
That way I can change the data if necessary.
Yep, we get the same value.
Same value? Okay, so what does that mean? It means that the exceed damping ratio is what? Is lower than 1.
Which means it's underdamped.
So it means it's an underdamped system. Perfect. Which is the case which is the more interesting. So underdamped system. So let's see, if you go to the printouts that I just gave you, instead of just redoing the whole derivation, even though we could, but what should be the response for the underdamp? When you're also, let's say, from handout, we see that x of t for the underdamped system is equal to exponential of minus the damping ratio omega sub nt times with the initial condition x of naught cosine omega sub dt probably it's not going to fit on this line, so I'm going to put on this line, plus x dot naught plus c x of naught divided by omega sub d sine omega sub d d. So it's not here on the page, on the summary of results, but if you want, you can write it down. You can add it to the page. What is the damp frequency?
It's the square root of xi squared minus 1 all times omega n.
Is psi squared minus 1, yeah. Times omega n. Really, no, sorry, this is, you see, is 1 minus psi squared, otherwise it would be negative, no?
Indeed.
Sorry for that. It should be 1 minus xi squared. All right, so what can we do? What can we do now? So, okay, so we can do now is to try to print it, to go and print it. So, this is the expression we have. So let us go to, let's say, MATLAB, and let's print it. So, home, I guess I go to computer here. All right. Now I log into my account. This is logging in. You let me know. Maybe I don't know if it will be more clear. Can we turn the lights off just at the front or not? Or we just turn all the lights
Yeah, I
off?
think so.
It might be.
It might be. We might be able to get more contrast on the monitors. Well, they go side by side instead of.
Nice.
Maybe try that.
Yeah, that'll probably be the better one of the two.
Maybe what up a little bit. If you need them for writing, let me know and I'll put it back. Just trying to think about. So log in here. What did I do that? Okay. So you need to come here and tap MATLAB. So to me, I don't use MATLAB that much anymore at all, so every time I come back, there is a new version or something, so. But I mean, the function's basically always the same. Okay, yeah, it's a bit different to what I'm used to, so personally I don't like those things here. If you like them, you can keep them, but. So here, what would I do? I don't know, I do this one, I do the old style. Maybe. Okay, come here to a new file. I don't know, we do it by line. Okay, so Johnny, every time I start a MATLAB file, I always do clear all to clear all the variables. I clear the screen. And then basically start putting the data of this program. So what do we know? So let's say this will be, I'll give you this file afterwards. Okay, example 1, for example. It should be on the class notes more sample files, but I think doing it together will help. So n equal to 200, k is equal to 1000. And you can merge as much detail as you want, but I'm not putting that much. C equals to 100. Okay, probably we need that variable, so omega we know is equal to the square root of k over m. So xc, the damping ratio, is equal to c divided by 2 times m times omega. Okay, we can check this one, we can do it. And the response, so let's say t, I'm trying at the beginning, so x, let's say 0.01 or 0.1, 0.1 should be enough. To, I don't know, let's say 20. I think that's the one on the figure. That's the one on the figure. So x, because this one, x1 for, yeah, x. will be equal to what? Exponential of minus xc times omega times t times the first one, which is x sub naught, oh, I need to put those ones, times cosine omega d times t. We need to define the variables, but I'll do that at the end. Plus, let's put it in parentheses, x sub, but 4 instead of 0. That's the velocity, so v naught plus xc times x naught divided by omega d times sine. Oh, this is different than what we did in class, no? So times omega d times t.
Professor,
Yeah.
I think you forgot an omega in the parentheses where it says VO plus XCI.
Okay, let me go back. So let's go back one by one anyway, but before that, maybe I want to define what is, now you can, I probably forgot something. Omega d, we know is equal to the square root SQRT of 1 minus xc squared times omega. Okay, now let's check this one. So let's check the first term. So this one looks correct. This one is x sub naught cosine omega t. Is that what we have on the okay, the flat note? So that one looks correct here, no? Plus d naught divided by omega d times omega dt. Is that what it is, or?
I think where it says XCI times XO, there should also be an omega in there.
Oh. Okay, I didn't put it on the. Okay, so let's check. Let's check the response over here with the handout that I give you. I was just looking at this equation here. I was just looking at what I wrote, so did I forget to put it over here as well?
Yeah, I think so.
So let me check that page. So on the damp, yeah, correct. So here should be also an omega n. All right, thank you. So let me go back then to the computer. Times omega. Okay, and now all you have to do is type plot tx, and then it will put like x label. In this case is time in seconds. Oops. Probably better than me at MATLAB because I don't use it much at all. And this would be, let's say, analytical response or solution response. So it will be x of t. So let's see, run. Oh, I need to save it first. I think I created before coming to class a MATLAB folder here. I'll give you the file, I will put it on Canvas, but this is just for me, so I don't have to redo it all the time. Yeah, I did that today here. All right, so this will be example just let's call it. Oops, why do I want to type it? So example, let me just put this free damping. No, okay, so here we go. Oh, forgot to put that stuff over here. we forgot to put initial conditions, so here we need to put initial conditions, so let's put them over here. So all the initial condition, this was what, 5? I think the initial
Yeah.
velocity was 1.
Yep.
We have a problem, so what is the problem now? Line 17, inner matrix dimension. Oh, I get it. So I think the problem here is going to be, okay, so do you see what the problem is in here now?
You
Because
need to
all
do
these
it-
ones are just one value and t is a vector.
Yeah, you need to do it dot times.
I need to do, and that's what I think it is. You need to do the dot time over here, probably here as well, and here as well, no?
Should be.
I think that should do it, but I don't know. I did it more
Oh, maybe also on the XCI and the exponent?
in here.
No, to the left. Where at the beginning of the line you have exponential
Yeah.
negative XCI dot times, maybe? Yeah, make that, put a dot there maybe?
I mean, we can put it everywhere, would be the safest, but.
No, alright, it doesn't work.
Generally, the way I will do this, let's remove them and then I will show you the way I will do it, but I'm pretty sure we need some of them over there. In order to know what that is, generally I will first take the first term this way. I will go here and see if it gives me a problem. It does not give me a problem, no? Looks like it's doing it.
Okay.
So, I don't know. So maybe it's doing between both of them. Let's see what I will do if I take off this one. Is it doing it? Okay, so one, doing the other, but the other wants to do both of them. Okay, so maybe I just need to have one in the here.
Yeah.
Don't ask me why I needed to do it that way. You see, just try and error, no? But generally, is so. I mean, here you can adjust the time. If we, I mean, 20 seconds looks maybe too much. We can do maybe 10 or 15, whatever you want. So you see, the response starts at 5 and is damping basically after 1, 2, 3, 4. After 5, 6 cycles, it's almost staying at a very low value, no? Okay. So, and if you want, generally I like to put it, this one, I don't know if they still have those commands, but I like to put grid. I think you don't need to put the on, but I like to put the on. And basically you get the same thing while it's not grid. Any idea? So maybe you don't have to put on. Or maybe I need to put a different location. That might be the fun thing. Oops. Put it at the end. Okay, no one wants to do it. So forget about it then. Okay, I thought it should do a grid over here, but it's not doing it. Okay, so this was the analytical response. So now we're going to see how we can find the numerical response. So let me close this. Let me save this file here. I think we already saved it. And let's go back now to the .cam. And let's work over here. No, please send them for me. At least I can read it. Okay, so now I will put over here. CMaple file. I will put in Canvas, but basically, yeah. When we kind of plot it, yeah, here, X, so this was the time, this was X. I think, where do we start? We'll start it on top, Let me go back to that one. And computer for a second. Oops, we'll run this one. So what was the initial condition is x0 was 5 over here. So that's from where we start. And you see that right away it doesn't go down to 5, but it kind of go to -3, or between -3 and -4. It kind of go here. Then it stays somewhere here. Goes up back to 3. It's down here a little bit more. So 1, 2, 3, this one, and then basically now it really starts getting damp very quick. All right? So you should be able to see that figure. From the, may I give you the MATLAB code so you can write? Okay, but just want to give the general shape of the response. Okay. So now we're going to do why does it show twisted? Because my page is lined up with the side of the wall. This is not straightened. So numerical okay, so this is really what is useful for you guys. Okay, so the first thing to do is to rewrite the equation of motion in state space form, which basically means in function of the displacement and velocity. Okay? So I'm going to give you just the general form of the mathematics. So generally you will say, first step would be to assume y is equal to x dot. So what's the problem that we have? Is that on the initial equations, what is the order of the differentiation for the x that is multiplied by m? It's mx double dot, no? So we need to make that one x dot, correct? So what would be the way? If this is x dot, then the one will become what? Y dot would be like writing m y dot, no? So it would be the double dot. So that's a bit the idea. So you do this, and then you say, imagine that z, this is just what I'm trying to do, this is x and x dot. All right, well this would be what? This is the initial displacement, and this would be our initial velocity. Okay, and that's the main reason why we need to write under this form, because our initial conditions, the beginning of our solution, are going to depend on what? On the initial conditions, which are the displacement and the velocity. Okay, given over here. All right, so we know what would be z dot.
Would be x dot x double dot.
X dot, correct. Y dot, but that's exactly what it means. Or this will be x dot x double dot. okay? And just one more if you want. What is x dot? It's y, x over dot. So this is not complicated, okay? I know it might look, the first time might look a little bit complicated, but so now we say recalling the equation of motion, which is what? M x double dot plus cx dot plus kx equals 0. So this we can rewrite as x double dot plus c over m x dot plus k over m x equal to 0, or what is more important over here is that x double dot will be equal to minus c over m x dot minus k over m x. Okay, so now look at this term of here of the equation. Okay, this one, yeah, this one or this one, whatever you want, these two, and look at this equation. So then we say this is the assumed function. So the function z dot becomes what? What is the dot? If you look at this figure over here, is
X dot.
x dot, correct? And x double dot will be what?
Negative c over m x dot, negative k.
Negative c over m x dot minus k over m x. And this is added because this is the way it's programmed, but okay. What was z over here? Did you think about it? What is it z? What is really z? Z is initial displacement, initial velocity, no? Yeah?
Yes.
So basically this one here, so the initial velocity is z2, meaning is the second term. All right, if it was like a matrix, a vector, would be the second term. And this will be what? Minus cm z2 minus k over m z1, no? So if you want to be part of even more details. So from here, really this means that what? Z1 is x sub naught, Z2 is x sub naught 0 or V naught. Okay, this at the beginning looks a little bit strange, but once you do it 2 or 3 times, it's pretty straightforward. Okay, and I think I give you the class notes anyway, so you should have access to them. so let me go to a new page and let's try to do the programming. Okay. So for the analytical solution, again, I will give you those printouts. Maybe I'm gonna have, sorry. Phone. Okay, so let's go. Maybe to make it more clear, I'm gonna, could I mix it with this one? I can probably mix it with this solution. Yeah. So let's say this will be, let's just change a bit the nomenclature, then we do everything. So it will be X analytical. We can call this one X analytical. All right? So the conditions will be the same. Let's see if we can use the same time, maybe not. Let's see, it would be figure, we'll see the figures at the end. Okay. So, well, then we should be able to combine this. Okay, so maybe let's change this a little bit. So for us, Z is what? The matrix will be X naught, B naught. This will be a row, this will be a column, or a column. All right, so we have this. Now the important thing is to create the function where we created all those z dot equal to z2 minus so on. So new, can I do it here? Yeah, let's do it. New script. Okay, so generally this will be a function, so differential function. I'm going to use what I have on the class notes a little bit. I might change a little bit. Right, so we're going to create a function. F, which is going to be the function. You have it as the function 1, okay, of T and Z. I'm surprised why I'm doing it that way. Okay, we're going to try to do different stuff because it's different. Let me try. We need the data what? T, Z, M, K, and C, I guess, or XC. No, we need
C should be fine.
C should be fine, yeah. Do we need omega? Probably omega. Okay, M. I don't think we need the damping.
You'll need X naught and Z naught, or more.
Yeah, we need the C. So basically this would be the time. Notice we have T and Z. We have T and Z on the original one. Z is this. T is this one over here, no?
Mm-hmm.
Let me move the time up so we don't put it at the wrong place. So let's say T will be here. And now, let's go back to this one. So this will be T function. So now the T function, what we want to do is what? So this would be like saying the Z, so F equals zeros. Should be 2, 1. Now we're going to have, 2, 1. The vector. So we know that F1 is equal to Z2. This is our Y function, okay? And then that F2 will be equal to minus C divided by N times Z2 minus K divided by M times Z1. I think that's all we need for this one. Let me see what I've done here. That's really all we need. I think so. All right, so now this is our function, the function 1. So we go to here. I now need to call the function to solve it. So we'll solve for t, comma, z. This is the part maybe a little bit confusing, which is going to be here. ODE 45 is the numerical method we use to solve, which is called the ordinary differential equation solution 4.5, which is the Runge-Kutta function. So the function we're trying to solve is what is d function 1. All right, so it looks like, oh, you're asking us for the, so you can click on this. So it gives us direction. So T-span maybe this could be T, so comma T, that should work. And then we need the initial condition, which is y sub 0, that for us should be what? Z or which is those two conditions. So it should be, wait, so it should be Z, should be Z. And we'll close this. Can you put the parentheses on both sides on that one? No. Function is fine. This one will need that either. And T. Okay. All right, so let's see what happened over here. Probably something is going to go wrong. All right. Solve and name OD is function. Error in OD 45. So what can be the error here? Right, let me just to try to spot the error. Probably it's nothing to change anything, but this span here, if I look at this page that I'm using to follow, but that should be exactly the same thing. I don't know why.
Is defunct1 supposed to be a string?
The what?
The argument defunct1, is that supposed to be a string?
This one is in, oh, we didn't save it. Probably that'd be the problem. So this is, maybe it doesn't know where to go, so I guess save as, it should solve it as the function 1. Yeah. That might be just the problem, huh? You don't know where to go.
Try taking the quote marks off of defunct1 to see if that does anything.
Okay.
Okay.
I was just looking at what I have here on this one. So it looks like on the first one, I mean, this can be picky. I haven't done this for a while.
No, it looks like the problem's actually in the defunct1 file. At least I'm reading that error message correctly.
File, yeah, line 6.
Yeah.
All right, so line 6.
Oh, looks like in the Z parentheses.
Oh, up at it too, yeah. So this is Z2. All right, so I guess I need to save this one first, then I need to get out. Let's see what happens now.
Yeah. I don't think
So this is on the ODE function, and then line 17, so that one looks good. Okay, I don't know why, but
I
sometimes.
think if you just take off the quote marks, it should work now.
This one, okay.
Give it a try.
I'm just gonna go up and put items.
Now is the errors on D function 1.5.
Okay.
Do we change the value for Z on this one? No, let's see. But let me go here, what is Z over here? 5.1. All right, so let me look at something here. You see they changed the stuff, now I don't know what to do. How can you create to debug this one? All right, let me try one thing because maybe it's just a simple case. So maybe it might just be this. So T-span here, the way I have it set up on this page, so it'll be different, but the result should be exactly the same. It looks like it needs to put as a vector, so it will be from 0, let's say to 0.1, to what was the time we used before, 20?
Mm-hmm.
To 20. That should not change anything. This is the same as this,
Should be.
but let's see if that will change anything. All right, so the other thing, the function TZ, that's probably what it is. The function, what do you have over here? Let's go back to these ones here. I know what can be here. TZ and KC. No, this is fine, so TZ.
Yeah. Looks like it has something.
All right, if to tell the truth, I don't know if that's gonna be the case, it should not be, but when I did the one on the notes, I redefined this one inside. And you should not have to do this, but let's see that with the prime M equals 200, K equal 1000, C equals to 100. And then, so I don't have to define these ones, the only output is gonna be T and Z.
I think the problem is in the main script file, when you write defunc1, you don't put the arguments in. I think it needs
Yeah,
to.
they don't have them initially, that's why I'm trying to do this now. So in here,
Yeah.
defunc1, I'm solving for T and Z.
Yeah, but if you take off the quotes and make it defunc1 open parenthesis T
Oh.
comma Z, I think that's what it's supposed to be.
Yeah, I think what happened is that, you see, this variable is this one, so I think maybe this is not helping at all that well. So T-span, and then Z. I think before maybe we had T and T, you see, output for input,
Mm-hmm.
and we get confused. Okay,
All right, cool.
but that's not the figure, but we got the output because this is the figure from before, not the analytical. So now, let's see what we have over here. So let's see what is T. T is just the time, okay? So how can we plot this? I mean, you should be guys the experts on MATLAB. So subplot, number 1, 2, 1, 1. We do the first figure. Subplot 2, 1, 2. So it looks like we're gonna have T and then Z should be two functions, no?
Sure.
Velocity and the one. So we want 1Z1, no? No, Z2. So, I mean. All right, let's see what happened now. All right, but maybe I did something here without using what I did. So what is Z? Looks like Z is two vectors, no? So what should be on the Z? What should be on the first one? Z should be the
Positions?
Where do we have Z located here? Everything should be here. So yeah, Z1 should be the positions here with T, no, is the output of the function f, which should be the position, and then the T2 is the response to the system, no? Yeah, the minus m over 2z. So that's why we go and print the second column of the output vector, and this will be, instead of being the analytical, this would be the numerical response. So they will go, and here basically you see that, it's funny, that one goes reverse over here. Why are they not the same? Why are they not exactly the same? Here is strange because it's damping at the same rate, no? It's only initially. We have 5, it should start from 5. I think we have that correct, no? 5 and 1. Where was x over here? Z is 5 and 1. Look at what happened here. They should be identical. Why is the second one not studied at 5? Let me see. We put the function here. Okay, maybe there's a lot of difference here because this is the same function here, t, z, reduced period, see that would change something. See what I mean? I'm not trying not to have redundant variables, no? What is the figure now? Maybe this function. Okay, I don't get it. It looks like this is pouring here from 0, but it should actually go from there, no? This is like shifted.
Yeah, it looks like it's shifted.
It just shifted.
And
The same was shifted. I mean, you will see, Johnny saw the 3.5. This is different orders. I don't think. No, 31.45. Oh no, there is 3.2, okay. It might be. All right, so let me see what can be the difference here with the one that is online, the code. So 5.1, 5.1. TZ or D45, T function, T span. Z0, this would be the initial conditions this should be using. Okay. What is omega? Is omega 0.118? Okay. The XC. This span 0.1. Probably that doesn't change anything. I don't see why they're not identical.
Can you look at the function file for a minute?
Is something with the data different?
400,
400, 1100. F0 is to 1, F1 equals to 2. F2 equal to minus Z over M Z2 minus K over M Z1. No
maybe,
idea.
Maybe could the apostrophe next to the 100 be doing something? I don't see why it would, but
Oh,
maybe.
you never know.
Yeah.
You know, the problem is that we use a function which is the ODE for 5,
Mhm.
and now is the problem that, you know, if they change something on it, no,
Nothing.
no there. So, I don't know what to tell you. Because the solution should start from the Z0 here, it should be the solution, so. Let's see over here, the only thing I can say here is to type like help ODE for 5 and see what is the order of the command. So you see this will be like the function, and this should be the initial condition, so let's see ODE for 5. All right. T-span y of 0 initial value. So the ODE function will define T out, y out. The T-span will define, and this is the initial conditions. Why is that not? Which is what we have defined. What can be the difference point? 0.5. Oh, maybe that might be 0.05. So that's 20. Oh, maybe that might be the problem. If I do that, I'm going to have to change something here. And then what happened here? Okay, no idea, guys. So, I don't know if they changed something on the ODE45 function. But basically, really, this part, I'm not going to say it doesn't matter because it should be identical, but what matters at the end is to know what is going to be the response after a certain time, no?
Mm-hmm.
Okay? So you see basically that in either case, it looks like the response will be dumped out within what, 15 seconds? Okay?
Mhm.
So I don't know why it shifted over here. That's very strange. Let me look at something here.
In the function, does any part of the function reference Z1?
Yeah, this one.
Okay.
Which will be K, if you think about it, K M over M is like the static deflection, no? Almost. Was Z1. Let me look at something, let me close this here. Because I think I got it the same way. And let's see if I have the function here on the class notes. I'll give you both files. So ME400 cost material. So I guess, do you see that files over here?
See a couple.
What is this? The function looks like it's this one here. Figure analytic numerical. So let me try to open these files over here. I don't know, analytical. Oh, it's not going to open from here. So, how can I do this stuff
This
now?
looks different.
I cannot put this one that the columns will be on the side. No idea, or, you know, like instead of being up and down, it will be side to side. What is this? Parallel? I don't know what I'm doing here. So.
It might be under the View tab.
View.
Yeah, left, right, top, bottom.
Okay. So Analytica, this is. Oh, this is the analytical, okay, okay. Oh yeah, this is using the, okay, no, 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 one. It's correct, but I don't know. Okay, now close everything. Alright, so. Open analytical, open. This one. Sorry for that. I know that when things don't go smooth, you can get a bit more confused. So, no. I cannot go back here. Course material, looks like exercise 11. Exercise 11. Okay. Looks like this is, oh, this is 10.5 KCD1 DT. This is the same thing that I use over here. OD for 5 T-spine Z0. This is the same thing, no? Can I run this one and see what it gives us?
Sure.
See if we get exactly the same one. So figure 1 would be, oops, figure 2 doesn't do the other one. Beyond just, oh, so this is the, okay. So it should only give one figure. It's just, this one I start from 5. Why is this not, like, what is that doing that? I mean, let me look, can you, let me look 1 second because I don't know if that's the example 11 or not. This is exercise 7. So I don't know what I'm doing here to 11. Alright, 5. Open. So this is not 11. 11 looks like there is some type of random. How can I go back here? So you see somewhere exercise 7, 13. 9. All right, so I don't know, what would be this one here? Right, so let's try to open the one before, maybe I see what is wrong. Course material. How can I exit this? 100. Summer. MATLAB. Right, 2 more minutes and it doesn't work. Is this what we have on the class notes? Or was it reverse?
I'm pretty sure that's what was on the class notes.
Can you please check with your class notes? I can go here and check, but because the only thing I'm thinking is that, you know, the sine and cosine have been reversed over there.
Yeah, looks right.
That's right, that's what we have on the class notes?
Mm-hmm.
All right, so then, I don't know. Let's go here. So I'll do it down. trying to find what is the response here, exponential on the gram. Oh, I don't have it on the dot form anyway, so. Yeah, I don't have that one. Okay, so this, I'm not surprised, is cosines. Times something. Okay, let me try just this for a second. No, but sine. Huh. I'm not going to change anything, but. All right, let's try, otherwise I will have to. Same problem as before, no?
Yeah.
Okay, guys, so let's keep going. I will just look into it, okay?
All right.
But what I was looking at here, okay, what I was trying to base, which I think those things you have them with you guys. Let's see. When I was looking at the course material, chapter 1, the example we're doing is almost there. This one here, no? Okay? I didn't copy exactly these ones. You see this is a lot longer, but I was going through the MATLAB code, that's the one I was looking. So this is 5.1. You see, that's why I changed the date. It's a little bit different because I go to find 20 seconds. So this is the T max. This is basically the code for each one of the cases. All right, it will do for each one of them, but you don't need to do that. And I was trying to find what is the expression if it were exactly the same one. But you see here, I use the exponential notation, no? Instead of the sign. So x equals exponential minus c omega t. C1 omega t. Okay, so cosine, this is the cosine, this is omega d. So cosine sine is the same one we had in our code?
Mm-hmm.
Cosine sine, no? So that's the same one, and this would be the velocity. So this is dx1x dx. Yeah. Alright, so basically I was looking at this. This is what I was using also as a reference. But I was trying to do everything a lot faster. Okay? The function 1. And I was looking here at the outputs. So if you look at the outputs for the analytical solution and the Runge-Kutta, they are identical, no?
Mm-hmm.
Okay? And same thing for the velocities and this.
Mm-hmm.
Let's try one. I'm sure it's not going to be the answer, but I'm just trying something. Let's see if they change something on this. Huh. so ask me why, okay? But it looks like they changed something on the OD, so here the one on the Z, you need to go to the Z one. Okay, on the first column. Instead of this one. Now you see they are identical.
Yep.
Okay? So maybe let's look at, so we spent about 10 minutes turning around, and then one simple case over here. So let me just try one thing here. I know it doesn't have to do anything, but let's say this would be figure 1. Figure 2. Plot then Z1, Z2. See if we do it. Why did I do that?
Oh, looks like on Z1, is that a square bracket?
Oh, yeah. No plot anything, no? Okay, so, I mean, this is driving me crazy, this monitor here, so let me see what Z is. But you should plot something, no? Let's try
Oh,
here.
wait a minute.
Plot Z1.
I think it should be Z colon comma 1 and then Z colon comma 2.
Yeah, because just plotting just one value.
Yeah.
Yeah, right.
There we
Okay, and that should be the image of the test plot, no?
go.
So the one, since I'm gonna do it, so this would be X label. Should be, let's say, X for position, and Y level. Even it looks like they're reversed now, but should be velocity. I know there's a way to do an X dot, probably there's a way. Okay?
Mhm.
So now you have this one, so let's get it. Let it put your position. Okay, guys, so now you have the figure here for the phase plot, and you have the one here for the response. Okay? So be careful, because it looks like they changed something from the previous MATLAB versions. These nodes have are at least 10 years old, so MATLAB, and they may have changed something, okay?
Mhm.
All right, so before we move on, let me save this file. So we sum it on the MATLAB and give them to you. So here, no, not here. And where do I go? Where do we decide to put them? So do I create another announcement with MATLAB files or something?
All right.
Because we're probably gonna have to have more MATLAB files. Files, upload, choose. Summer. Open, upload. All right, so let's say now, let me go into Abstract. Stay here. And save. So let's go now, this one here, and let's create a new assignment. So everything is on the class notes, basically homework. 2, 1 point. Due date, I'm just gonna put a date, but randomly, okay, let's say Thursday. Right. You can always change it. Then unpublish, I don't know why I need to do it that way. Never let me publish at the beginning. So something we can do, I don't know how we solve, but I'm gonna say write a MATLAB code that for a given input data values for N, C, and K, will determine if the response is critically damped, overdamped, or underdamped. the dam. Maybe that doesn't look too good. Okay, it's 3. So write a MATLAB code that for given input data values for M, C, and K will determine if the response is critically damp or not. And then we'll solve the problem. We'll solve the equation of motion. And analytically, and numerically. Basically, it's what's on the classes, no? But try not to copy and try to make your own MATLAB code, okay? To learn it. Then output should include side by side or top and bottom, okay? Whatever, side by side. Side by side. Figures of displacements for analytical and numerical solutions. Do you understand what you need to do? Basically, it's what's over here. I'll show you over here on this MATLAB code, which is on the class notes. I mean, what you want to do? If you really don't know MATLAB, if you copy it, at least you're going to learn something, but try to make it better, okay? Something that suits you better, because the one's at least 10 years old. And you see that they have changed something here on the function, no? Because I define the functions as it is over here, and it looks like when I go to plot it, I plot Z2 on this one, and now it's Z1. So what is this one? If you see over here, Z1 is the time, and D2 is the position, so I don't know what I did. But it should be Z2, no? I put time over here, and then Z2 over here the first time, and now it looks like it's reversed, so be careful. No, this is the face plot. So this one, we have to put Z1, no? For it to make it work. And you look over here that in that time I put Z2, no? That's why I use Z2, so I don't know. I don't know if they changed something on the ODE. Okay, guys, so it's important that you learn the MATLAB, because once we move to 2 degrees of freedom, there is no way for me. There is a way, but it takes a long time to solve all the eigenvalue problems, to solve them by hand. MATLAB will do it in a second. Okay? So that's it for today then. So I think you have enough time by Thursday to do that homework. Also, if you want, guys, this morning before coming to class, I look at the homework you submitted online, the first homework. I give you a grade. I put some comments. Overall, I know the solution was on the class notes, but I was paying more attention to really see if you were following a good procedure and you were showing the work clearly, no? Mm-hmm. So if you did not do that, probably I didn't give you 100, and I put that comment. So look at it. Any questions about today's class? Okay, and I think you had to take a MATLAB class, is that correct?
Yep.
Okay. I know generally people are programming that either they like it or they hate it. There's no in between. So, but I'm going to tell you something. Myself, I never programmed until I did my PhD. The only thing I programmed was my calculator. I knew how to program my calculator. And I had to do big programming and I had no idea, so I had to learn everything by myself. So. And all my work was computational.